Okay, let's do this thing. This is setting up the hydrogen atom. I'm not going to solve the hydrogen atom, okay? I'm going to get it into 4 differential equations, and some of those I am going to solve, so I just lied. This is complicated stuff, but it's super important because it's really the only real atom that we can solve exactly or get an expression for exactly. So let's just start from the beginning and get going. This is the Schrodinger equation. This tells me something about the wave function psi. The wave function has to satisfy this condition. So this is the imaginary number I, this is a constant h bar. The partial of psi with respect to t is related to, this is actually the kinetic energy term, that's a momentum operator. Negative h bar squared over 2m, that's the mass of the particle. Del squared is the Laplacian, which I'll show you in just a second. There's that wave function again, and that's the potential. And so the potential I'm going to use is the electric potential energy of a hydrogen atom. So I have a proton, an electron, and they're separated by a distance r. So the potential energy only depends on the distance. Negative e squared over 4 pi epsilon naught. So e is the charge of an electron. One is positive, one's negative, so we get a negative sign here. And that's the electric constant. And then 1 over r is the distance. Okay, so there's a lot going on here. First of all, suppose I have some wave function psi as a function of, let's say it's t and r, where r is a vector, right? Because it has really 4 pieces here. If I did this in Cartesian coordinates, this would be a wave function of time, x, y, and z. We're going to use spherical coordinates because we have a spherical potential, but let's just imagine that is the case. The first thing I want to do, I want to get 4 separate equations here because this depends on time. This is a spatial derivative, so I have really 4 things going on here. I want to get them all separated. Okay, so let's just first off assume that I can write this function as some space function of r times some time function t. So suppose I can write it as a product of functions. If I do that, I can put that in up here. So if I put this, I'm just going to write this lowercase psi and some function lowercase f. I'm going to put that in up here. Well, if I put this in for psi and I take the partial with respect to time, it's not going to do anything to the space part. So I can just pull that out front. So I get I h bar psi. I'm going to leave off the r part. That's a psi. Partial of f with respect to t equals negative h bar squared over 2m. Now again, this is a spatial derivative and it's not going to depend on time, so I can pull the time part out front. F del squared psi plus v psi f. Now the trick here is to multiply both sides by 1 over psi f, and if I do that, this is going to cancel. I get I h bar 1 over f partial of f with respect to t equals negative h bar squared over 2m 1 over psi del squared psi plus v. Now, if I make the assume v only depends on r, it does not depend on time. If the potential does not depend on time, does not change with time, then this part of the equation only depends on r. This part of the equation only depends on t. So if I have this only depends on r, and r changes, and it is equal to this, and t changes. The only way these two can be equal is if they're both equal to the same constant. So we can call this constant e. And that just has to be true. So let's set this equal to e. I get I h bar 1 over f partial of f with respect to t equals e. Now I can divide by I h bar and multiply by f, and I get this. The partial of f with respect to t. If I equals f over h bar, yeah, and then I have divide by I, but if I multiply the top and bottom by I get a negative 1, so this is negative I. So this says, what function can I take the derivative of and get the same thing? Oh, then there's an e. Take the derivative of with respect to time and get the same thing back with a constant in front of it, and that's an exponential. So right here I get f of t equals e to the negative I e t over h bar. If you take the derivative of that, I get the same thing with this negative I e over h bar. So this is my time-dependent part. And that's cool and all. Again, it depends on having v as a function of space only, no time dependence. But now I have this other equation, which is the time-independent Schrodinger equation right there. And now we want to solve that. So this happens all the time. I want to go over it again because I think it's useful, and I like it. So I'm getting another piece of paper right here. So let's write down where we're at right now. So I have negative h bar squared over 2m 1 over psi del squared psi plus v equals e. And this is the time-independent Schrodinger equation. Yeah, that's what that is. Okay, so now we want to do something like what we did before. I want to separate this into a space and separate this function psi into multiple parts. So I have to deal with this Laplacian. The Laplacian in Cartesian coordinates looks like this. The second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z. But if my potential depends on just r, that one variable, this won't be able to be in just one of the groups if I do it with x, y, and z. If you do a zero potential for a particle in a box, then I can say psi is some function of x times some function of y times some function of z, and you can separate everything out. Okay, but we can't do that here because the v term would have all those x, y, and z in there. So instead, I'm going to switch to spherical coordinates. So I'm going to use the spherical coordinates that look like this. So here I have some location. This is the distance r. This is the angle theta. And then this is the angle phi. Just so you can see that. And in that case, the Laplacian looks like this. I'm looking at my notes because I always forget this. 1 over r squared, the partial with respect to r squared, the partial with respect to r. So you have to actually take your function, take the partial, multiply by r squared, and then take the partial again. You don't get a nice simple thing like that. Also for the next term, I get 1 over r squared sine theta, partial with respect to theta, sine theta, partial with respect to theta. And then I get plus 1 over r squared sine squared theta, theta, second partial with respect to phi. That's the only one that actually is kind of nice. So that's my Laplacian. So with that in mind, I'm going to actually break my function psi into two parts to begin with. I'm going to say psi as a function of r is going to be some r function times some angle function, which I'll call y in terms of theta and phi. So if I put that in here, then this is only going to operate on the r. This is only going to operate on y, and that's only going to operate on y. But let's put all that in along with this. Trying to think. Yeah, let's just do it. I'm trying to think. Let's multiply through by psi. So I'm going to get negative h bar squared over 2m del squared psi. Actually, I'm going to not do that. I'm going to multiply by psi 2m over h bar squared, so I get del squared psi equal, I'm trying to decide if I should do plus. Let's just do plus. Plus, no, it's going to be minus. Minus 2m over h bar squared psi v, remember v depends on r, equals negative 2m over h bar squared e psi. Okay, so now I can take this partial derivative, the Laplacian on psi, which I'm putting in as r times y. So I have this first term. It's only going to operate on the r part, so the y can come up front. So I get y, and then 1 over r squared, partial with respect to r squared, partial of r with respect to r. Now, if you're just listening to this, you may say r, and yeah, see, but I'm writing little lowercase r and capital R. And then I have this term is only operating on y, so I get, so the r can come up front, so I get plus r over r squared sine theta, partial with respect to theta, sine theta, partial of y with respect to theta. And then again, the r term can come out. I get plus r over r squared sine theta, second partial of y with respect to phi. And then I get minus 2m over h bar squared r y v equals negative 2m over h bar squared e r y. Now, just as before, the next trick is to divide both sides by ry. So let's do that. So let's just put this as parentheses, 1 over ry. Actually, no. If I do that, I'm going to get rid of this y. That's good. But right over here, I'm going to get rid of the r, but I'm going to have an r squared. And I want to get all the r's with one term. So here's an r squared, here's an r squared. So I'm actually going to multiply this by r squared over ry. Yep. Okay. So if I do that, this term, the y's cancel, and I get r squared over r, 1 over r squared, partial with respect to r squared, partial of r with respect to r. And then I'm going to move this term over here too. This term is the ry is going to cancel. So I get, but not that. So I get minus 2m r squared over h bar squared v. Yeah. Okay, so now this term is going to be equal to the r squared is going to cancel. The r is going to cancel, so I get plus 1 over y sine theta, partial with respect to theta, sine theta, partial of y with respect to theta. And over here, the r squared r is going to cancel also, so I get plus 1 over y sine theta, partial squared with respect to phi of y. And then I have that term, which I'm going to put with, I'm going to put this as, this is the same term as this. So I'm actually going to write, I'm going to add this to both sides, and I get, I'm going to put this as v minus e for right now. Just keep those together. Those have the same terms in front of them. So I think that's right, v minus e. Let's see, wait, let me check. Minus, yeah, because there's a minus sign. I bring that over and it becomes, okay, that's good. And so this is equal to 0. And so now I have this only depends on theta and phi, and this only depends on r. So again, if these two terms add together and they equal 0, but this only depends on r, and if r changes and this doesn't change and they still have to add up to 0, that means that this whole thing has to be equal to a constant. And this has to be the negative of that constant. And so we're going to, now here, there's a couple tricks. There's multiple tricks in this thing. Okay. And the trick is that we're going to call this constant L times L plus 1. And you may look at that. And I thought, in the past, I've said, okay, I'm just going to call that some constant B. It gets way more complicated. This makes things much easier. So this is the case where once you solve a problem, you know a better way to do it, and that's what's going on here. This is looking ahead. This is using clairvoyance. Okay, either that or intuition. But if you don't do this, it makes it really complicated. If you do this, it makes it nice. And so if that's the case, then this would have to be equal to negative L times L plus 1. Okay, so we have an equation that just depends on r, and an equation that just depends on theta and phi. And they're both equal to a constant, so that's good. Let's go ahead and handle this r stuff first, and then we'll come back and handle that. Okay, so if that's equal to a constant, then I get the following. R squared over, and I just want you to know as I'm writing this out, there's probably like a 58.2% chance I'm going to make some fatal error in this calculation and just not even post this video. So if this video does indeed get posted, it's like the multiverse where this one particular thing happens and I got it right. So if you do this on your own, you make a mistake, that's normal. Okay, there's a lot of stuff going on here. It's easy to lose track. Oh, here I have that canceled. So just so you look right here, I'm writing this term, but I have r squared over r squared, and those cancel. I can't cancel with that one because that's in the partial. Oops, sorry. Okay, so I have 1 over r, partial with respect to r squared, partial of r with respect to r, minus 2m r squared over h bar squared, v minus e equals L times L plus 1. I'm just double checking. And yeah. So I'm going to go ahead and multiply both sides by r. And I get partial with respect to r squared, partial of r with respect to r, minus 2m r squared r over h bar squared, v minus e equals L times L plus 1 r. Now, this is a differential equation that only depends on r, but it's not a good differential equation because I don't have the second derivative of some function. I got to take the derivative, multiply by r squared, then take the derivative again. And that makes it really difficult to deal with. And I don't want to deal with that. Okay? So we are going to, again, use another trick. And here's the trick. I'm going to define a new function, u equals r times r. And that means that r equals u over r. But if I substitute this in, then I'm going to need to take the partial of this function r with respect to my new function. Okay, and then multiply by r squared and take it again. So I'm really going to just work on this piece right here. So let's do this. So the first thing I'm going to say, I'm going to actually write this as u times r to the negative 1. I think better of derivatives that way. I don't like, it's something I can remember. So let's do this. Let's take the partial with respect to r, of r with respect to r. So the partial of r with respect to r is going to be the partial of u times r to the negative 1 with respect to r, right? I'm just replacing, instead of r, I put in my u times r to the negative 1. So if I take the partial of this, I have a product. So I need to take the partial of u times that plus u times the partial with respect to that. So I'm going to get, first of all, the partial of u with respect to r is just u with respect to r, and I'm going to multiply by this. So I get 1 over r partial of u with respect to r. Now I need to take the u term and take the partial of this with respect to r. So the derivative of r to the negative 1 is going to be negative 1 over r squared. So I get minus u over r squared. Is that right? So I take the derivative, so I bring down the negative 1, I reduce that by 1, and yeah, okay. So now that's this part. I just did this. Now I need to multiply by r squared and take the partial again. So if I multiply this by r squared, I can write r squared partial of, I'll call it u r to the negative 1 with respect to r. I just did that, but I need to multiply by r squared, so I can get r partial of u with respect to r minus u, because the r squareds cancel. Now I need to take the partial of this with respect to r again. So the partial with respect to r of r partial of u with respect to r minus u, is going to be, okay, I got to first do a product rule right here. So I'm going to take the partial of the r with respect to r times that. The partial of r with respect to r is 1. So I get the partial of u with respect to r. Now I need to take r times the partial of u with respect to r with respect to r. So it's going to be plus r times the second partial of u with respect to r. Now I need to take the partial of this with respect to r. So I get minus partial of u with respect to r. Oh my goodness. Look what happens here. Isn't that amazing? I have a partial of u with respect to r and a minus partial of u with respect to r, and they cancel. So I get r times the second partial of u with respect to r. And something, I mean, that's pretty important, right? Because we went from a first partial times a function and then taking the derivative again, which is not good, to just a single second partial derivative. But now we're in a function of u. Okay. So, I mean, we've done the u equation. Let's just put it all together. So if I can put this in for that, and then I need to put in, right here, r, I need to put in u over r, and that's u over r. Okay, I need a new piece of paper. So let's write this out. I feel like I'm going to make a mistake. I feel like I'm at the point where I'm going to make a mistake and not even know I made a mistake. But that's fine. So this term goes that's right here. Oops, you can't see that. This is that term. So I get r times the second partial of u with respect to r. That was that whole term. And then I get minus 2m r squared, and then I have an r, which is u over r, and then over h bar squared. And then I have v minus e, and remember, v depends on r. And then I'm just looking at I'm looking up here. And then I have equals L times L plus 1 R, which is U over R. Okay, so let's go ahead and multiply through by R. I get, I'm trying to think about which, actually, let's divide through by R. I think I made a mistake because I have R. This doesn't. U divide by. This is U over R. I feel like. Oh, there's an R squared term right there. Oh, that can't. Okay, that does work. Okay, so that cancels that. I divide through by R, and I get the second partial of U with respect to R minus. That's minus 2m over h bar squared v minus e u equals L times L plus 1 u over R squared. Yeah. So that's not a function, that's not the R function, that's a function of u, but it is a differential equation that we can solve, at least try to solve. Okay, so I have the second partial of u with respect to R, and they have u, and they have u. So this is something that's doable, at least. Maybe difficult, but it is doable. And my goal here is to do this numerically, do that one numerically, but not today. And remember, L is a constant. We don't know what that is, but we're going to get that from the next part. Okay. Whew, moving right along here. We're done. No, we've got 2 equations. We have 2 more to do. And one of them is a doozy. Okay, so let's go back to my angular part over here. This is all my angular stuff. I'm just going to write this out. So I'm going to say, I'm going to multiply through by y. So I get 1 over sine theta, partial with respect to theta, sine theta, partial of y with respect to theta plus 1 over, shouldn't that be sine squared theta? I think this should be sine squared. Yeah, I'm going to say sine squared, but now I'm not so sure. Yeah, it's sine squared. So 1 over, where was I? Sine squared theta. Second partial with respect to phi of y equals negative L times L plus 1, and then I had that y term. I multiplied through by y. Okay, so that's my function. Now, this depends on two variables, so we're going to do the same trick. I'm going to say y as a function of theta and phi is equal to f as a function of theta times p as a function of phi. Now, a lot of times, if you look at other solutions, they'll say, oh, it's theta as a function of theta and phi as a function of phi. But I just don't like that. I don't like writing this capital theta. It makes me a little angry. And so I just choose capital F because you know why. There you go. If you don't want to write it, this is a variable. You do whatever you want, right? So let's put in FP for every place we see y. I get 1 over sine theta, partial with respect to theta, sine theta. Now I'm going to take the partial with respect to theta so the p doesn't do anything. So I'm going to bring the p out front and then have the partial of f with respect to theta. And so this is a double thing right here, just like before. And now this one, again, the theta term is going to come out. So I have plus f over sine squared theta, second partial with respect to phi of p equals negative L plus 1 fp. And what I want to do is get two terms where one term only depends on theta and one term only depends on phi, and then I can do what I've been doing the whole time. Now, we have a problem here because there's a sine squared theta in this term. So if I multiply both sides by sine squared theta over fp, then here I will get something that only depends on p. And that means that this will only depend on theta. So let's do that. So right here, the p's cancel, and I get f, and then I have a sine squared divided by sine. So I get just sine theta, partial with respect to theta, sine theta, partial, oh, that's 1 over f. Partial with respect to theta f. Now this term I also multiplied by a sine squared theta fp. The fp's cancel, but the sine squared doesn't. So I'm going to add this to both sides and include it with this term. So I'm going to say plus sine squared theta L times L plus 1. And then this term is just going to be plus the f is going to cancel, the sine squared is going to cancel, 1 over p, the second partial with respect to phi of p equals 0. So again, this stuff only depends on theta. This stuff only depends on phi. The only way those two things can add up to be equal to 0 if they're equal to the same constant. Now here's another trick. This one's not too difficult to see why we do this, but I'm going to call this constant negative m squared and this one m squared. And so this has to be equal to negative m squared. And let's take this term and write that as a differential equation, and then we'll save this one for last. Okay, so here is my equation. I have 1 over p, second partial of p with respect to phi is equal to negative m squared. I actually can solve this differential equation. So let's multiply both sides by p, and I get the second partial with respect to phi of p is negative m squared p. So the question is, what function do I take the derivative of twice and get the same thing back with this negative m squared? And the answer is an exponential. Okay, you could write this in terms of sines and cosines, but it's going to work out much better if you write it in terms of an exponential. So let's just guess a solution. Let's say if I guess p as a function of phi is equal to e to the negative m I. No. E to the negative I m phi. Well, if I take the derivative of this once, the partial of p with respect to phi is equal to negative I m e to the negative I m phi. Cool. The second partial with respect to phi of p is going to be equal to negative. Oh wait, this is just I. Negative would work. So then I get I times I is negative, and then I have m times m is m squared, and I get e to the I m phi, and then that is my p. So it does work. But if in spherical coordinates, phi goes from 0 to 2 pi. So if I start at phi is equal to 0 and I go all the way around to phi is equal to 2 pi, I should have the same function. I can't have a different function at the same value of phi. So let's say phi of 0 equals phi of 2 pi. So let's put that in over here. So I get, right here. So I get e to the I m times 0 equals e to the I m times 2 pi. That should be true. So this is 1, right? Because I'm raising it to the 0 power. And now what does that say about m if this is equal to 1? Well, I mean, this is something that we can write this e to the I as a function using the Euler formula. So e to the I theta in general is going to be equal to cosine of theta plus I sine theta. But you see here I have no imaginary part. So that means that I have to have cosine theta is equal to, or cosine phi has to equal 1. So cosine of this has to be equal to 1. So cosine of m2 pi is equal to 1. And that is only true if m is equal to 0, plus or minus 1, plus or minus 2, and so forth. So that puts me limits on m. And those are my m quantum numbers. Okay, that's 3. We've solved 2 of the equations. One of them we didn't. We have one more, and we're not going to solve it, but I'm going to write it down. Let's go back over here to my f equation. I'm going to write that one down. Okay, so I get 1 over f sine theta, partial with respect to theta, sine theta, partial of f with respect to theta, plus sine squared L times L plus 1 equals m squared. And m can only be, we already said m only has certain values, and that came from being equal to the phi part. Okay, so this is a complicated equation, but it does have a special function solution, and I'm not going to go over it, but this is the Legendre functions. But there is one important thing from this, and because we have this L times L plus 1, then it is in the right form, and that's why we put L as L plus 1, because of this theta part. So I do want to say one thing about this, and that is that this, in order to make this work, the solutions this work with, that's a constant between some negative something, an integer. It turns out that L has to have parameters too. So L from the solution, L can be 0, 1, 2, 3, and so forth. And then M, because it has to do with derivatives, and you can't take a derivative more than, it has to do with polynomials, and you can't take a derivative of power more than that polynomial, then M can be anywhere from negative L up to 0 to positive L. And that's, those are your quantum numbers, and those are important. And yes, I didn't solve this equation. I didn't solve the R equation. I did solve the phi and the t equation, but I did separate the Schrödinger's equation into 4 differential equations of a single variable, and that is a big deal. And I admit that there might be a mistake in there somewhere, and if I do, I totally apologize. I don't see the mistake, so I'm going to post this video. This is the one version of the multiverse where I actually do get that. It's like beating Thanos when doctors... This is an Avengers reference, and if you know that movie, I'm just going to leave it alone. So, okay. So I do want to come back and solve the radial equation numerically, but I'm not going to do that in this video. I wanted to set this up. Hopefully you find that useful. I'll talk to you later.